is a great program, I feel, for all high school students, and it really makes seeing molecules much more vividly and offers a lot of options both to the student and the educator. You can see right here I'm drawing a methyl group, and I'm going to come up here to 3D optimize. That makes all those bond lengths to the correct size, taking into factors like electronegativity. The program allows you to rotate the molecule both on its own, or you can also free rotate it, and I will show you that in a moment. This is showing different types of models the program can create. The ball and stick molecule I feel is most often used during this age group. You can really see the molecule the best, and then also you can see the different types of colors, and it doesn't get too bogged down by other factors like the size, shape. However, it will be useful, and I can show you in a situation where that will be relevant. Here I'm taking the bond length. You can see that the molecules that are measuring are turning green. So that would be the bond length of oxygen to carbon, and this is the bond length between carbon to hydrogen. You will notice that those are different because oxygen is much more electronegativity than hydrogen, and therefore it holds its electrons closer to carbon than it would to hydrogen. So this is a very different molecule. This is an ionic molecule, and this is between a metal, sodium, and a non-metal, chlorine. And you can really see that the bond type is very similar. However, they're very different. So bond length there, and these guys actually is very different. Covalent molecules will actually share their electrons between each other, and ionics have a tendency to grab each other's electrons and take them from there. So here, as you can see, you can change the background color, you could change the atoms colors, so you could change the chlorine to any color you wanted to, the sodium to any color you wanted to. And so just demonstrating the versatility of the program here. As you can see there, I opened up a periodic table, so you can choose from any molecules on the periodic table, which is very useful as you go kind of freelance in it to create your own type of molecules that are on the sidebar there. And so here you'll see I'm taking the charge, and I have to make it negative to make the molecular shape that I want to, because that accounts for the lone pairs of the molecules. And here you can see it's a triangular bipyramidal molecular shape, and you can see that that's characterized by 3 molecules around the center atom. The bond angle there are 120 between them, and then you have the axial carbons, which are in 180 to the bottom. So again, I'm checking the bond length. You don't have to do these for all fluorines, however, I will show you that they are the same, which makes sense because it's a completely symmetrical molecule. So then again, I'm going to go back in, find that xenon again, put that down, and I'm going to create the exact same molecule. However, this time instead of a 5th fluorine, I'm going to put a hydrogen, and we are going to observe how this affects the bond length. So this is a great kind of a tool for students to use as they're looking through different types of bond lengths and bond angles, and how do just the type of how molecules affect that. And you can see here I forgot to optimize, and so pushing that button then optimizes the molecule to the most stable 3D structure. And so you can see that the fluorines are far apart as they can to each other, and then the hydrogen is very close to the fluorines. And so again, checking how that bond angle changed from removing that 5th fluorine and replacing it with the hydrogen. So then we can ask a lot of crucial questions to students of why it changes and that type of thing. So here we're going to look at we're going to use carbon as our central molecule, and then look at halogen size. And so I'm going to put different types of halogens decreasing in size on this molecule. However, I am going to get an error here as I try to make it, and this is just to show the versatility of this program. So it denies me and says that the molecule that I put on there will not bond to carbon, and therefore it has to be removed. So remove that, and then I will replace it with a different halogen, iodine, just a step above that. And it also told me why that does from a chemistry standpoint, so that was a really great tool of the program. And so then optimize and draw this program, or draw this molecule, and you can really see the different size quantities of the molecule. If I wanted to, I could go in and change the iodine and bromine's colors, so those two would be very different. However, right now they're both green, which gets a little confusing. And then this would be the time when you would use that sphere kind of optical model representations, because you can really see how much of the space that those molecules take up. So I'm going to go back to ChemDraw, and we are going to create another molecule. This is going to look at different types of bonds. So as you can see right there, I drew a triple bond, and as you go to draw a quadruple bond, which carbon actually can't form, it erases it and then goes back to the single bond. So again, just another way to check it. And so here I'm going to draw past the octet of carbon. So you can see that the program puts a little tiny X through carbon and then tells me it's a -2, so which means that carbon wouldn't form. So then I got to go to Control and undo that, and I'll do that here in a second. So again, another way that the program actually goes through and double checks students as they create these different types of molecules. So there we go, I undo it, go back, display those explicit hydrogens, and then there we go, we got our molecule. Go up, grab the lasso that up, and then we want to include hydrogens in the models, and then here we go, we have a very nice linear model. And again, those carbons should be very well close to each other. We could also change this, we could do different types of bond lengths by different types of bonds. So single bond, double bond, triple bond, and how that affects the bond length. So this would teach students about the trends of those molecules and how the different type of bond affects the bond length of those molecules. So I'm going to grab another carbon molecule here, and we're going to add to it. I'm going to add a fluorine, go up, again display those explicit hydrogens, and then we are going to double bond an oxygen with a fluorine. And so we're going to look at how bond length is affected by having 2 electronegative molecules compared to just 1. And so this is really kind of a hard concept for students, especially at first, of how dipole-dipole momentums, one of the intermolecular forces, affects shape. And so this is a really great 2 models to really kind of teach that concept and really make sure that it's really ironed out between those 2. And so as we observe the bond length, we see that the fluorine and oxygen kind of act as like competing forces for those electrons, whereas in the one molecule with just fluorine, it can grab all those electrons to themselves. And so we see a really radical difference between bond length there. And so this is just an example of the real power of this program. You can see here I'm just going to draw a program on the right side of basic things and then kind of mix them from the left and just kind of draw a molecule freehand and really put it together really smoothly, really simply, and it gets big really quick by adding those pre-made molecules to the right. And then you can also see, that it does the free pairs, does everything for you, puts charge on it. And so really relative, very easy to use program. We're going to put a few more carbon groups here, finish up here, and then we're going to lasso. And then right down here you can see that it says the FW, which is the formula weight, and it does that for all compounds. So students will actually be able to see the molar mass of what we call it as chemists, or formula weight. We call it both. But students would not have to calculate that, or they could calculate it to see how accurate they are compared to that. And so that is the 3D representation of that huge molecule. You can see that carbon bonded acts as kind of a bridge between the 2 benzyl groups there. And so very interesting, just kind of free-handed molecule, really showing the power of what that program is capable of.